Alright, so let's look at this question here. So to get shots of a car flying through the air in movies, it is sometimes necessary to drive a car off a cliff and film it. Suppose a stuntman drives a car off a cliff 10 meters high at a speed of 20 meters per second. How far does the car land from the base of the cliff? Alright. So looking at this, how far does the car land from the base of the cliff? We're looking for range. So how far horizontally the car goes. So let's use our problem-solving strategies and start by sketching our situation. So we've got a cliff, alright, and we have a car that's going to launch off that cliff. What we're told here is that the car launches straight horizontally, right? It drives off a 10-meter high cliff. So if we were to draw its trajectory, right, if he starts off horizontally, he's going to take the shape of half a parabola before he lands on the ground. Alright. Just for convenience sake, I think it'll be convenient to call the base of the cliff and where the car kind of starts as our 0, 0. And let's set up our coordinate system so that positive y is upward and positive x is rightward. Again, you're free to call your zeros and your positives in whatever direction works for you. It'll affect your initial condition values. Alright, so this is a 2D problem because the car is both moving horizontally and vertically. So we need to worry about two lists of our kinematic variables. We have to list what's going on horizontally. Oh, sorry, I'm having trouble writing. Man, my pen, the plastic, really broke off the nib, so that's better. Alright, so I'm just going to list horizontal and then vertical. Alright, so horizontally we're going to use the x-coordinate system where rightward is positive. Alright, so I'm just going to list kind of all the variables I need to think about. So we're dealing with position. So you have initial position and final position. We have velocity. So you have a horizontal initial velocity, horizontal final velocity, acceleration, and then time. Right, so similarly for vertical, we've got our initial y position, our final y position, initial y component of velocity, our final y component of velocity, vertical component of acceleration, and time. Alright, so let's start with the easy things. Let's look at initial position. So looking at our diagram and our prompt, the important things, the two moments in time we're worried about, or not worried about, but that are going to be useful to us, is going to be the starting location when he just drives off the cliff, because we know information about that. We know that's 10 meters high, and we know his speed there. And then the other one's going to be where he lands on the ground, because we want to know how far the car goes. That's going to be that distance there. So, initially, horizontally, we define that to be 0. And our initial vertical height is a positive 10 meters. Where the car lands horizontally, that range we don't know. In fact, that's what we're solving for, so I'm going to circle that to remind myself that. And he lands on the ground, which we're defining to be our 0 height. Alright, so position's done. Let's look at velocity, particularly initial velocity. So our car drives straight off the cliff. So at the beginning moment in time here, our velocity vector, if we were to draw it, would be completely horizontal. Right? So in the velocity here, since this is what I like to call horizontal launch problem, but the initial velocity vector has no vertical component. It is entirely horizontal. So although I wrote that this is v naught, we can also say that's v naught x. So he drives off the cliff at a positive value of 20 meters per second, and there's no vertical component of that. When we get into problems where perhaps instead of launching horizontally off the cliff, maybe there's some sort of ramp and it's at an angle, we're going to have to deal with this initial velocity vector and break it up into x and y components, but we're pretty lucky here. Now, horizontally, when the car lands, we do not know that velocity. If we're kind of looking at our trajectory here, that velocity, though, is going to be at an angle, so to speak. So, what we do know, though, is information about acceleration, right? So then I'll jump back to velocity in just a second. So acceleration, we know that since the object's in free fall, we only have the acceleration due to gravity, which is straight down. So it's only in the y direction. So our acceleration vertically is negative g. Horizontally, there's no acceleration. Therefore, horizontally, our velocity doesn't change. So if our initial velocity is 20 meters per second, the horizontal component, the final velocity will also be that value because, again, there's no acceleration. So then for velocity, we start at 0, but we don't stay at 0 because it is accelerating vertically. Right? So we expect that our final velocity be some negative value because the acceleration is negative, but we do not know what that is. And finally, the time it takes to go from the initial to the final location, we do not know what that is, but what's going to help us out is that these are the same. Alright, so we want to solve for the range. So we want to solve for our final horizontal position. Alright, so we narrow it down to two kinematic equations. We have the position equation, which needs time, so we can't use that right off the bat, and then we have the no time equation. So looking at the no time equation up top here, what's annoying if we plug in our zeros is that acceleration is 0, which means this entire term here goes to 0. So the no time equation, all it tells us is that our horizontal final velocity is equal to our initial horizontal velocity, which is what we already knew. So basically we're forced to use the position equation. Alright, so we're forced to use x naught plus v naught x times t plus 1/2 our acceleration times time squared. Again, plugging in zeros, our horizontal component for acceleration is 0, and our initial position is 0. So we're left with our final position is initial velocity, the horizontal component times time. Alright, so we can use this if we knew time, but we don't know time. So the way we're going to solve for time is, well, we can't use the horizontal material to do that, so we have to look at the vertical values to solve for time. Alright, so we're going to use vertical to solve for time. Alright, so we need to choose an equation to do that. So let's use the position equation. Alright, so we have that our final y position is our initial y position plus our initial y component velocity times time plus 1/2 our y component of acceleration times time squared. Plugging in zeros, initial velocity is 0, final position is 0, and let's see, plugging in other constants, our acceleration is negative g. All right, you don't have to plug that in until later, but I'm going to plug it in now because it's a symbol. So that gives us the expression 0 is equal to our initial y position minus 1/2 gt squared. All right, so it's nice that this term was 0, because then we have to solve a quadratic equation, which is fine, but just more tedious. Rearranging here and solving, we end up with the expression that time is equal to plus or minus the square root of 2y naught over g. So I got that by just doing a little bit of algebra. So plugging in our numbers, I'm choosing the positive value because time is never negative. So we have the square root of 2 times 10 meters divided by our 10 meters per second squared. Sorry, there's like a million announcements this morning. Anyway, putting this in our calculator, I'm going to round here to 2 sig figs. I probably shouldn't do that. 3 sig figs might be better, but this is what I have written. So we'll go with it. 1.4 seconds. So that's the time it takes. So now we can use this 1.4 seconds in our expression above. So we have that our final position is our initial velocity horizontal component, which is 20 meters per second, multiplied by the time it takes, 1.4 seconds, which gives us a value of 29 meters. So that's how far our object travels horizontally. So this is how typically these problems are going to end up. Odds are, if you have a problem, particularly what I like to call a horizontal launch problem, you want to think about and define your coordinate system, which way you're calling positive. You realize that the horizontal and vertical motion is independent of each other. So horizontally, there's no acceleration. Vertically, there's acceleration of negative g, or positive g, depending which way you're calling positive. But and then you list your knowns and unknowns, and typically you're going to have to use, if you're trying to solve for something that's in like your horizontal list, for example, then you're going to have to use the vertical information to solve for time, and vice versa. Very typically, you're solving for time and then using that time to then solve for your other information. All right, so I hope that was helpful.